Good evening. Before I begin, I have an announcement to make. There's been a little change in the schedule. So this talk called Writing Your Application, this is PC04, and this was originally scheduled for Thursday. And so we swapped it with the talk that was here. Originally, it was called Unlocking the GPU with Direct3D. So in case you came to listen to the D3D talk, this talk is highly applicable to you, and I'd encourage you to stay here. And as you can guess, I'm not talking about the windows in the sky, and I'm not talking about the windows in the pocket. I'll be talking about the one on your lap and the one on your desk. And my name is Anantha, and I've been at Microsoft after doing a bunch of research in virtual reality. And throughout my career in Microsoft, I worked on various releases of DirectX and 3D graphics and graphic subsystems in Windows. And today, my role is that of a group program manager and responsible for the graphics and desktop subsystems in Windows. And what never ceases to amaze me these days is the rate of innovation in graphics. I remember back when I was in grad school, I would ask my advisor to buy a $100,000 SGI machine to do the kind of graphics that this guy can do today for less than $1,000. And the other thing which I'm always amazed about is the ubiquity of graphics. So back then, people had to buy and install additional graphics cards, mostly if you were a gamer or if you wanted to work on workstation applications. And today, this is ubiquitous. Like even a netbook class PC has pretty powerful graphics. So in my talk, I'm going to be talking to you about how, in Windows 7 timeframe, we are broadening the applicability of the DirectX APIs to enable you to take advantage of this powerful and ubiquitous hardware in any application that you choose to write. So the agenda goes like this. So my talk has got 3 sections. So in the beginning, I'll just talk very briefly about where the graphics hardware is headed and what we are doing in Windows 7 to adapt to these hardware changes. You got a little glimpse of that in the keynote today, which Steven Sinofsky was doing. Then the second section, I will talk about the expanded role that DirectX is playing in Windows 7. And the last section, I will talk about the new scenarios that are emerging because of the advances in the hardware. And these scenarios are not tied with one particular API. They transcend APIs, and they cut across all of them. And I'll be showing how you can take advantage of them or make your application work in those scenarios. So yeah, I'll get started talking about where graphics is headed. So today, the GPUs, when we think about GPUs, the best way to think about them is that they're simply a massive array of SIMD cores. Think of them as a bunch of SSE units or something even bigger than that, just ganged together. There's large numbers of them. The highest end out there has 800 of them today. And they are very general purpose. They have fully IEEE compliant floating point math. They are all capable of general purpose flow control. And you can do pretty much whatever you did on the CPU today almost. And there are still some fixed function units, such as for tessellation. And the other very interesting characteristic of all these GPUs, and this is a little bit of an eye chart, but all I really wanted to call out is the size of the bars there. So this is a quick snapshot of all the hardware that is available from NVIDIA, for example, in the last quarter. And you can see there's an order of magnitude difference in performance. This is a chart that shows performance over a bunch of benchmarks and averages them. So there's an order of magnitude difference between the low and the high end of the graphics hardware today. So pretty vast disparity that does not exist in the CPU land. Even the lowest end Atom processor is pretty close to what your Xeon can do. Now, we started putting the GPU to much broader use in Windows itself, starting with Windows Vista. In Windows Vista, there was a bunch of the user interface that started using the GPU. So for instance, the Media Center and the desktop UI through the window manager was using it. The video playback, of course, always needs the GPU horsepower to be able to do higher resolutions. And Windows 7 continues the usage of GPU from there. The place where we have made the biggest changes in the usage of GPU continues to be in the desktop and the UI that all of us use every day. So in Windows 7, the window manager itself uses the Direct3D 10.1 API. And If you remember, in Vista, we already made it work from all the way from a low-end integrated graphics in a laptop to pretty high-end multi-GPU machines. And we continue to do that in Windows 7. So we, in fact, make the DWM work, the window manager work, in far more cases in Windows 7 than it did in Vista. In Vista, if you remember, there were many cases where it would shut down. One of the important things that we did in Windows 7 is we actually cut down by a huge amount, by 50% per window, the total amount of system memory that each window is using in the window manager. We make much more extensive usage of the shaders, which is basically code executing on the GPU to implement our glass. So that gives us much more customizable glass. And if you saw the keynote that Stephen was doing today, and if you attended Chaitanya's talk in the afternoon over lunch, where he was showing the new taskbar at the bottom of Windows 7, there's a lot more richer animation that is going on. And there's not just animation. So you even see that there are different types of highlights. There's almost like a little spotlight that is being cast on each of those icons. And all that is being done on top of the GPUs in Windows 7. So in the area of displays, we connect to a variety of displays today. And the big changes that are happening in this time frame are high DPI and high color. So high DPI displays are extremely common. So we talked about that in the keynote. And so here's a little chart where I just simply put together the common sizes of laptop screens and the common resolutions that are out there. And as you can see, there is a range of DPIs all the way from 97, 96 to 147. And it's a common assumption that all applications make that all screens are 96 DPI. And that's no longer true. There's a range of them. So in Windows 7, we are adapting to the various DPIs that are existent on the machines today. So we have made a number of improvements in the Windows UI itself, as well as in the Internet Explorer, to enable the experiences to work well at all DPIs. There's a lot of work that different teams across Windows and IE did to make this work. The other thing that we did is today, if you buy a machine which is a higher DPI machine, the text and everything tends to look like really, really tiny. So what we do now in Windows 7 is instead of end users trying to figure out how they can go and fix it, so we automatically configure it. The very first time you open the machine and you boot Windows 7, we actually set the machine up for the right DPI. So therefore, like when our artists have designed characters or text in the UI to be 9-point font, it looks like 9-point font, which is measured in inches, not in pixels. The other thing that we are doing, in case you or the rest, anyone else wants to trade off the higher real estate that is available in these higher DPI machines for the bigger text size or vice versa. So we have promoted the ability to use DPI to set the desktop zoom-in factor. And above there, in the slides above, first one is the Vista control panel, and the second one is the Windows 7. As you can see, like we are actually putting it right there so you can customize it. High color today is more and more common in displays. Just the other day, I was looking at the ads in the back of a newspaper, and TVs are advertised to have 130% or 150% of sRGB or of NTSC color space. So this is becoming a new way that the displays are trying to differentiate from each other. So, and that's happening because there's a number of advances that have happened in the backlight technology, in the emergence of new connection standards. Connectors like HDMI 1.3 or DisplayPort enable a higher number of bits to be transmitted between the computer to the display. The other thing is, of course, the prevalence of GPUs that can handle high color. So what is high color? So high color is actually wider gamut. So here there are two pictures here. So on the left is a little small triangle inside. The colored area is the entire visual spectrum that we can all see. And the little triangle is what is the color displayed in today's machines. And on the right is an upcoming monitor which has a laser backlight. And as you can see, the triangle pretty much covers the entire visual spectrum. And so that means that these displays are capable of displaying all the colors that human eyes are capable of seeing. And high color can also mean higher precision. Now, a projector like this is extremely bright, and even LCDs are very bright today. So when you show content that was authored for older monitors or projectors, you start seeing banding all over again. And finally, high color can also offer higher dynamic range. So our eyes are capable of seeing anywhere from the brightness of the day to something really, really dim and dark in a dark room. And monitors, of course, don't display that. And so these displays that are coming out have increasingly higher dynamic range. So in Windows 7, to address the issues of color, so we have an in-box color calibration tool. So today in Windows Vista, this is available only if you have Media Center or you have to buy one. So in Windows 7, we just built it in the box. And two, we have a Gamma LUT loader in box. Now, this enables you to be able to load color profiles that were generated either by the color calibration tool, which is in box, or from a tool that you have purchased and calibrated your monitor. Now, systems configurations are also impacting graphics. I mean, I see a ton of laptops everywhere. People even have laptops at home. And even more interestingly, so we all connect our laptops to either TVs or projectors or other displays. And now in Windows 7, as you saw in the keynote, we are trying to make it work much more seamlessly. And every laptop will have the same standard way to project on external monitors and configure using the Windows P key. So I just very quickly went over a range of things that we are doing to adapt to the hardware changes in Windows 7. Now, let's take a look at how you can take advantage of this powerful hardware. And we'll switch to talk about the expanding role of DirectX in Windows 7, where we provide you the ability to do so. So today, when you're writing an application, a rich client application on Windows, you have a number of APIs that you can choose from. You have GDI, GDI+, DirectX, and WPF. They all have different properties. If you're a native developer, native programming, if you're doing C++ code, then you would choose between GDI, GDI+, or DirectX. Of course, if you're doing C#, then you would probably either pick WPF or GDI+. The GDI, GDI+, and DirectX are all three of them are immediate mode, primarily rendering APIs, whereas WPF does more than rendering. It has a retained mode scene graph, and it provides input, focus, events, and controls. And DX and WPF happen to be the only APIs that are hardware accelerated. Now, that's good. So that's like a good matrix to see. You can, if you already know and you're using these APIs, so you probably already know which API to go after. But if you are trying to figure out from the scratch, if I'm writing a whole new application, how do I choose an API? So here's my guidance. So when your application needs to work on all Microsoft operating systems and the lowest common denominator functionality is sufficient, you would use GDI. But if your application needs a lot of richness and it needs to be built very quickly, and you are okay not having fine-grained control over hardware or performance or features, then you would use WPF. But when you need full control over functionality and performance, and you just need that blistering 3D, then you use DirectX. And in this talk, I'm going to be talking about the DirectX APIs. So originally, we designed it for games. And when we first released it in 1995, it was abstracting all the hardware out there. Back then, there were 15 graphics chip companies, perhaps. And we were also abstracting all the various operating systems that were present at the time. Originally, DirectX had a number of other components. It had D-Sound, D-Input, D-Music. There were a number of other components, not just graphics. And over time, the hardware in the other areas was not evolving as fast. And it was really the graphics hardware that was evolving. And by the time we reached DirectX 9, which is a very, very popular API, and which is today even adopted by Xbox, we started having people wanting to program directly on the GPU. So we introduced the concept of shaders in DX8 and DX9. They became really, really useful because you could actually use a C-like high-level language called HLSL to program directly to the GPU. And it also had floating point support. So when we were developing Windows Vista at the time, we took a look at it, and it was a pretty compelling feature set, and we started using it for our UI, as I mentioned before. And actually, already by then, we had, already in Vista, we started using the GPU to do more than graphics. So the photo gallery in Windows Vista actually does quite a bit of image processing using the GPU via the D3D9 APIs. But we learned a lot. And we found a ton of shortcomings in the DX9 APIs. And we developed the D3D10 APIs. It was a very clean design, and it was designed from the get-go to be for more than games. We spent an enormous amount of time trying to figure out the API overhead, and we actually measured in terms of clock cycles how much time we were taking, so we could give you back the time so you could use the CPU time for your applications. We also did another very important thing. Previously, the DirectX developers were OK writing hardware-specific code, but increasingly, as more and more people want to adopt the DirectX APIs, it was becoming very untenable. So so the way we spec'd D3D10 API was that there were no hardware caps. So every DirectX GPU that you have looks identical to you as a programmer. And we also refactored the infrastructure piece, which was built into D3D9, into a separate API called DXGI. And we did that because the rendering technology typically evolves much faster than the OS integration code, which is found in DXGI. So over time, what happened is DirectX became synonymous with hardware acceleration or graphics. So if you buy a PC today, or if you buy a graphics card, they explain on the side of the box the power, the graphics capabilities in terms of DirectX levels. So today, DirectX has come to stand for high-performance graphics. So we are already seeing broad usage of Direct3D today. I talked about the work that we are doing in Windows itself. And our typical developer for this API is someone who needs very good performance and very custom and rich rendering. So the people who use Direct3D are typically people who already have a retain mode scene graph inside their application and who are OK who are OK using and who don't need a separate framework to help them code. We have a number of applications that are using us. So using our API, we have the mapping applications, both virtual and Google Earth do that. We have UI and application frameworks. WPF is built on top of D3D9, and as well as XNA. User interfaces I mentioned, MCE, Zune, and DWM. And even workstation applications, which were traditionally using OpenGL, have started using Direct3D API. I have named a few. In fact, I thought it might be better just to have one of them come here and tell us about their experience using our APIs. And so I have Jean Buffet from Dassault System, who's going to come and tell us how they use Direct3D 10 and what they learned from it.
Good evening. So I'm going to show you 3D Live that is part of the family of the Dassault System product, all built on top of CATIA V6 visualization framework. And since ever, CATIA is built on OpenGL, and now we're running on D3D10. So, sorry. The purpose of 3D Live is to really allow project manager to have 3D search and 3D navigate upon the 3D product, and to really have the handle of their planification, to be able to imagine and to plan their development, and to make the right decision based on the 3D modeling data and, I would say, PLM information that we call for the price, the weight of the part, and to have all those kind of things inside the comprehensive 3D environment that allow you to collaborate with your partners to be able to make the right decision. So this is really the purpose of the application that is 3D Live, that is the foundation of all the V6 application. So now I will switch and see. So this is Windows 7. And this is 3D Live. 3D Live, I will first show you a quick 3D navigation. So this is a toy. And I want to go through the structure of this toy and really to have a comprehensive way of managing the fact that all my designers are delivering parts on that design. And if I need to really understand what's happened, I can really go through the detail of it and to show it and have all the information, to have some external preview, and all those things now running on the D3D10. So when you are there and you have access to what we call the PLM compass, and this element is also a 3D element. This is not WPF or any kind of Windows component. This is 3D. All the things that I'm showing you, except the frame, is 3D. So from there, I found my part, and I want to really understand the purpose of this part inside the full design. So I will get in place and now try to understand where is it, what is the purpose. And now we can really use some advanced rendering option just to make sure that, okay, now the part is well positioned and I can understand what is the purpose of that part. So from now, I can start having more interactive way of working with my partner. And I will try to use, in the PLM toolbar here, the collaboration stuff. And once again, I'm staying in the 3D environment, and I'm launching some 3D dialogue that allow me to have some chat integration, for instance. And this is behind, we have Microsoft Communicator. And we really experiment a 3D chat to say, okay, we are going to talk, we are going to exchange some image. We have a kind of heads-up display that allows us to take some screen grab, some geometric grab, to exchange some feature. We have a lot of tools inside, and we can really go through some specific option and to have a really kind of integration that really helps the user to be very friendly user interface directly in 3D. So now, okay, navigation is okay, and now I want to go through more mock-up style application. So from now, I'm just switching, and now I'm able to have my mock-up. It's no more navigation with plates. It's really the mock-up. And now I want to go in detail inside. And now we really go to the challenges of moving on D3D10 and say, okay, we are no more in the kind of nice word for gaming or showing something. We want to make CAD. And from there, we have to be able to display the correct level of design for CAD style application. And here, for instance, something that's very usual is to find an edge, make a measurement, okay, and to have some, once again, very cool interactive way to make some change directly in 3D. So I'm able to really understand my design and take the correct decision to say, okay, this seems okay, and I'm going to release the part and accept the project. From there, I can show you also these kind of things. This is the structure of the car. This is the way that is designed for a specification perspective. And this is also taking benefits of the D3D10 because you can see that the font and the rendering of the text is very precise and very nice and very efficient in that case. From now, I will go switch again and go back to the exterior of my car. And now I want to go a very specific CAD rendering feature with the hidden edges. And this is, for instance, if I'm going in detail there, I can show the dashed line become a correct line and then back a dashed line. And this is specific to the CAD visualization feature. And this is very important for us to be able to move on D3D10. We have to respect these kind of things. This is the core of the product that we deliver. So for now, okay, we'll get rid of toy and moving something more serious. And now I'm going to show you a plane, complete airplane in 3D Live. And this is a Dassault Aviation plane. And we can really go in detail inside to really see the design. And the complete structure is inside. with the correct optimization at the CPU level and the graphic level. And of course, we can have some interesting rendering, and we have some in-context information based on the selection to really show some part information for decision support. So this is what we call the next 3D generation for us. And this is the V6. So we'll just come back to the presentation. So for now,
The other one.
the other one, yeah, thanks. Oops, no, it was the right one. We repeat the 3D, but not the slideshow. So this is really, through this little demonstration, I really intend to illustrate the objective of Dassault system, that we really want to go through the frontier between the game level rendering, the first class rendering that we are able to provide also with CATIA V6, and to provide the best graphic performances, and also we have to match CAD constraints and to manage specifically, as I show you, the hidden edges, hidden line removal, all these kind of things that make the things running to create real part for real life. Now, just let me to finish to share with you the developer experience for the way of moving from OpenGL to DirectX 10. First, we choose to move at that time because before, as you said before, is really game-oriented and does not fit the needs that we have to provide a CAD-level application. So we were waiting for D3D10 and all the new features that I provide through this new API really allow us to go through all these dash lines, for instance, things, using intensively all the geometry shaders that are one of the main points that allow us to make the development. And there's also very useful for the link thickness. That is very important for CAD style design, and to have point on the edge, or all these kind of things that is very challenging to reproduce using DX10 without the geometric shell. And now we just finished, because it's true talk also, that this is really challenging to moving from an application that since ages is designed on OpenGL to move that on the direct D3D10 level. It's first a technical challenge, just you have to rework your application to take benefits of the fact that now you have a low-level API that allow you to re-optimize at the CPU level your application, and before you would just rely on the OpenGL driver to make the job for you. So you have to rethink the way that you develop your 3D. And then, at the end of the day, it's payoff, because you somehow take back the knowledge of your 3D in your hand and optimize all your whole application. And this is the end of the demonstration. Thanks.
Thank you, John.
I will start.
Where's the clicker? Thank you. So that was a demonstration of how the work that we put in during Windows Vista to make D3D10 to be applicable in a lot more area than games paid off. But graphics is not just 3D, and for everyday applications and everyday use, 2D text and imaging tends to be probably even more important. And as you saw in the application, this application actually did the Dassault system did a lot of work to get the benefit of the GPU, and they did all the work by themselves. They did a bunch of work on 2D, and they did their own text handling. They did a lot of work to actually make it work and be extremely seamless. Now, not everybody can do that. And also, we found there were a number of other challenges, like while we were ourselves developing that. And we took stock of the issues with the platform before we started Windows 7. And here's what we found. So in the area of 3D, while DirectX 10 was a great clean API, its challenge is that it is not available. And as you know, today, when on Windows Vista, it works only when there is D3D10 hardware, and it doesn't work in any other cases. For instance, if there is no hardware, or if you're running inside a service or remoted. If you're doing 2D on Windows, today the APIs that you would use are GDI and GDI+. The challenge with GDI is that it does not support anti-aliasing and alpha blending, whereas GDI Plus addresses those issues. However, it is not as performant as it needs to be since it's not hardware accelerated. For text, GDI is the main API that all of you use and all of us use. However, it is not up to date in terms of its feature set, and even the quality leaves a lot to be desired. For imaging, we made great strides in Windows Vista with the introduction of Windows Imaging Component, or WIC as we call it. However, there are still a number of formats that need to be supported. For device control, today we use GDI. GDI was invented in Windows 1.0, and the hardware reality then is not quite the same as today. Things like multi-mon were grafted in, whereas multi-GPU just is not supported by GDI. So what we tried to do was first try and figure out if we could evolve the existing APIs, and that's what we did when we had a very good foundation API. So for instance, in the 3D, we evolved the Direct3D 10 API, and we use Direct3D 10.1 as a baseline. For imaging, we continue to update WIC because that was a great foundation that we made in Windows Vista. And device control, likewise, we updated DXGI. However, in the areas of 2D and text, there was clearly a need for a much bigger overhaul. And therefore, we came up with two new APIs, Direct2D and DirectWrite. And we'll be talking more about these APIs, and there are more detailed talks on each one of these APIs. But before I go in more further, so I wanted to show you how these are all tiered. So in this diagram, I show you like how these various DirectX components relate to each other. The foundation of everything is DXGI and Direct3D 10, and Direct3D 11 continues to be a peer. And everything else is built on top of that. And as you can see, so in this diagram, I highlighted the APIs I'm going to be talking about more in detail in this talk with a lighter pink color. So the primary focus of DirectX APIs are application developers who have large Win32 code base and and typically this code base has plugin models, and you cannot evolve everything overnight. So we originally designed this to meet the needs of Windows UI, Internet Explorer, and Microsoft Office. However, we also think that many of you probably have similar requirements and would benefit from the changes that we have made in. So the philosophy behind DirectX APIs has always been that of this Lego blocks. So these are, we give you a bunch of components, and you build rich applications to fulfill the needs of end users. So the DirectX APIs continue to follow that. The new versions of DirectX APIs continue to follow that philosophy. So you can mix and match any functionality. If you use one API, you do not have to pull in all the other APIs. These are interface-based APIs with C and C++. We are looking into managed bindings for these APIs. We don't yet have any news on that. And they're all hardware accelerated. And they are immediate mode rendering APIs. So that means that you will have to build retain mode scene graphs for your applications in case you need that. But most important, because we are targeting applications that have existing Win32 code, a big investment was made to make it interop with older Win32 APIs. And we are making all these APIs available down level on Windows Vista as well. So let's take a look at each of these APIs one by one. So Direct3D 10.1, as I called out, is the foundation rendering API. And as I called out, the big challenge with Direct3D 10 was that it was not always available. In Windows Vista, you had to have a DX10 class GPU for you to be able to use that API. However, there's a huge install base of DX9 class GPUs, and with the prevalence of laptops like netbooks, DX9 continues to be around. So what we did was we came up with a version of D3D10 called 10 level 9. So basically, if you write a DX10 application, it should, and you use the subset of features that are available in the hardware, it should just work on older hardware. We also made it work when there is no hardware. For instance, if you're running inside a service, or if you're running in safe mode, or in any other cases where the GPU just doesn't exist. And our solution is called Warp. It's a complete software emulation. I'll just show you briefly like what it is capable of. It can render everything the hardware can render, and its performance is pretty good. So here's a sample that if you have downloaded the DirectX SDK, you are probably familiar with. It's doing a pretty complex set of pixel shaders, and it's running on hardware right now. And if I switch it to the software rasterizer, as you can see, of course, the frame rate will go down. That's simply because GPUs are specialized hardware to be able to that are designed to do graphics. It's running on the CPU, and as far as I'm concerned, it's perfectly usable, and it is doing everything full fidelity. The other thing that we found when we were developing our own software was the incompatibilities in the color formats between GDI and DirectX, and we fixed those as well. And the good news is that since the middle of this year, practically every PC that is sold will have a DX10 class GPU, and that's because DX10 is a premium logo requirement with Windows Vista. Okay, that solves the problem of current hardware as well as older hardware. Okay, but hardware continues to innovate, and then there is still change happening. For that, we introduced Direct3D 11, and it's a strict superset of Direct3D 10 APIs. So if you have learned and you have invested time in learning the programming model for DirectX 10, not much changes for you. It also runs on all the older generations of hardware, such as 9 and 10. We introduced a few new features in DirectX 11. Some of them require new hardware, and some of them work on older hardware as well. By far, the most requested and most interesting feature is the multi-threading support. So today, if you have a powerful GPU and you're writing a graphics-intensive app, one challenge that you probably run into always, most applications that we found are CPU-bound, and because the GPU is waiting for to be fed by the CPU. So using the multi-threaded support that we have added in the API, you should be able to keep the GPU busy and therefore get much higher performance by utilizing commonly available multi-core CPUs. We also have a couple of features that require new hardware support, and that is tessellation and subroutine support in the shaders. But in my opinion, an even more interesting usage of the GPU is to do more than graphics. With DX8, with the introduction of shaders in DX8, and with floating point pixels in DX9, people have already started using the shaders to do GPU or non-graphics usages of the GPU. With DX11, we've tried to eliminate even more barriers. In fact, you don't need to draw triangles to be able to use the GPU to do anything that you want to do. So you basically continue to use the well-known HLSL and Direct3D resource model to be able to do things like image processing or video processing. It's in fact embedded in the Direct3D API for that reason, because we feel that those are the areas where it's going to be most commonly used. So we have a whole talk on that. We'll go into much more detail. And Alison Klein is going to give the talk on unlocking the GPU with Direct3D. And that talk is on Thursday at noon. So I'd strongly encourage you to attend that. And there is also a talk on Thursday where we go into details about presentation virtualization, where we'll be talking about how graphics is remoted in Windows 7. So Direct2D is brand new in Windows 7. It is a rendering-focused immediate mode API, and you use it to render 2D bitmaps and text. It has hardware pipeline for performance, and it has a full software pipeline for availability. In fact, the software pipeline is also very performant. And the good thing about that is you can use it anywhere, even when there is no GPU or inside a service. Since it is built on top of Direct3D 10.1, it has a number of benefits. First, obviously, it benefits because of the hardware acceleration that Direct3D provides. The second thing, the second benefit that it gets out of that is since Direct3D itself is getting remoted, we can actually, your D2D app will automatically get remoted. And finally, the other big advantage is that interop between Direct3D and D2D is very simple. You can either use the same device, or you can share surfaces between these two APIs. Therefore, you can come up with these cool 2D UI the kind of things that Dassault system had to implement on their own by using Direct2D. You can also benefit from the multi-sampling anti-aliasing schemes that Direct3D enables. If you don't want to use that, you also have per-primitive anti-aliasing that Direct2D supports. So the printing support for Direct2D is via the XPS APIs, because we are sticking with the philosophy of having the componentized model. So unlike GDI, where you had to use GDI to do pretty much everything, so here, if you don't need to do printing, you just simply use Direct2D. But if you do need to do print, then you link in XPS and then start calling into the XPS APIs. In fact, we designed Direct2D to be very, very compliant with the rendering rules of XPS and other standards, to the extent that XPS itself uses Direct2D in Windows 7 to print in case there are no XPS print drivers available. So I'll show you briefly what we can do with Direct2D. So I mentioned that Direct2D is capable of XPS quality rendering, and it is very, very compliant with that. So we wanted to sort of see how far we can take it. So we got our intern to build us an SVG player so we could actually load up all the SVG content out there on the web to just see like what it looks like. So here's one. So I loaded up this image. And as you can see, as I zoom in, it maintains the fidelity, and it's all vector art. But this is just boring, static 2D stuff. And since we are the DirectX team and we have the game's heritage in our blood, so we thought, let's do something even more interesting. So we did this. And as you see, we are interoperating with Direct3D, and we can actually do 3D and 2D in all at the same time. Okay, so graphics is cool, and it's always fun to show cool demos with graphics. But at the end of the day, text is what most of us spend our time on computers. We browse the web, and we read email, and text is extremely important. So with Direct Write, which is new in Windows 7, we unlock a bunch of features that were not available in the past. For instance, thanks to all the OpenType support that we added in Direct Write, we can now enable you to do higher quality text with all the features that are available in modern fonts today. Direct Write is also international ready. So in Windows 7, we added a number of fonts and shaping engines and script support. So if you use the Direct Write API, you automatically get all the support that we have added in Windows 7. But even more interesting, in my opinion, is the ClearType advances. So with all the work that we have done in the past on GDI as well as WPF text, we have learned a lot, and we tried to improve further the text quality in Direct Write. In fact, this is the aspect of Direct Write that has got a lot of Microsoft internal developers very excited. We have a number of teams who are looking at trying to use that. And if you attended the WPF talk earlier, Kevin just had mentioned that they were using Direct Write to make the text quality in WPF better. And I'll show you briefly like what he's talking about and why it's actually cool. Generally, text demonstrations are rather difficult and challenging on any display, but I'll try. So here's an application that we wrote. Here on top, it's text rendered by GDI, and on the bottom, it's text rendered by Direct Write. So first of all, one thing to call out is in GDI, the text is always aligned with pixel boundaries. Therefore, when you're doing your layout of text, it tends to get laid out in sort of unnatural ways. And here is an example. So here I'll show you in the word individual, up there you can see the N and I sort of got clumped together, whereas down here in the Direct Write text, so very, very zoomed in, you can see that they're sort of laid out in a much more natural spacing. But OK, that's good. But even better way to experience like what the quality impact of Direct Write, let's animate them really briefly. So if I rotate, as you can see, the GDI text just cannot hold itself, and whereas you get paper-like stability with Direct Write text. And a couple of important points about direct write. It works with any rendering technology. You can put it on top of any API. But it works best if you use it with Direct2D because large aspects of text processing, such as blending and filtering, get hardware accelerated via Direct2D. I mentioned API interop, and this is really important if you have a huge investment in existing code and if you're planning to use, and of course the philosophy of DirectX is these Lego blocks that you compose together. So API interop has to be an important aspect for it. So all DirectX APIs interop with each other, Direct2D and Direct3D, various versions of Direct3D, of course DirectWrite with any of these APIs. Even more interesting is the DirectX APIs interop with GDI itself. And we put in a bunch of effort in Windows 7 to make the interop between DirectX and GDI to be much higher performance. So as you saw in the architecture slide that I showed you earlier, that GDI and DirectX are really like two parallel stacks that come together at very low levels in Windows subsystem, in Windows. So therefore, if you are using both these APIs, it is really important to not directly blit to the front buffer using GDI because these two are very parallel stacks, you can get like unpredictable results. The right way and recommended way to use the interop is via the getDC call in DirectX. So every surface in DirectX, you can actually call and get a DC from it, and you can use GDI to render into it. So we spent a little bit of time to make it better. So in Windows Vista, so this is simple DirectX. I have some pseudocode here. So when you create a render target, you create a video memory surface, you render into it and present. And when you get into the GDI code, you call the surface as getDC. So we make a copy of it and copy everything into it. And of course, you draw with GDI and then release DC, and it all gets copied, and the surface vanishes. So you saw that we incurred a little bit of temporary memory penalty by allocating the system memory surface, and then it took 2 copies. But of course, in Windows 7, we completely optimized that. So the DirectX is all the same. So we just masquerade the surface to GDI, and once the GDI rendering is done, it just is the same surface. So there's no copies and no temporary allocation. So we actually made it far faster in Windows 7. So there's a lot more detail we go into in the following talk, Introduction to Direct2D and DirectWrite. Leonardo Blanco and Cam Verbraet are talking on Direct2D and DirectWrite, and as well as interop, and they'll be talking tomorrow. There's also a hands-on lab for DirectX, and there are a number of modules, including DirectWrite, Direct2D, and the interop. So I would strongly encourage you to attend those. DirectX is all about performance, and it's bread and butter. So we do a lot of work in our implementations, and we work very closely with the hardware vendors to make it very performant. But performance doesn't come for free. There's a bunch of work that we all have to do. So if you are writing a DirectX application, a very important thing for you to remember is to scale graphics content with the hardware. And that's really important because if you go back to the original slide I showed you about GPU performance characteristics, they range very, very widely in performance. So therefore, it's very, very important for you to identify a min bar and then try and tier and bunch together your features which are aligned with the hardware capabilities. We, for example, in Windows Vista as well as Windows 7, we do that for the window manager itself. So when we are running on a low-end integrated hardware, we turn off transparency and we turn off a bunch of animations. And of course, when you're running on a more higher-end hardware, we turn them on. And games tend to do that as well. And it's really important for you to come up with a strategy about how you're going to do that. The other important thing when you're writing interactive and high-performance graphics application is to always respond. The main loop should only do input and rendering, and it should not be mixing any network I/O or computation in this loop, because that would be detrimental to the performance of the application. Here's another interesting secret that the game people have learned, which is have a benchmark mode in your application. Now, let's say you do all the good work that I'm suggesting here in the first 2 bullets. Your performance of your application will get better even after you released it. And this is not the case for applications that are very CPU bound or CPU dependent on the CPU. For instance, when the clock hertz in the CPUs was going up, most applications did not benefit from that. And that's completely different in the world of GPUs, where because of the data parallel nature of that, they can make it faster and faster offline. So having a benchmark mode, which is showing us, as well as the IHPs, the typical usage characteristics helps us a lot to tune when we come up with the next generation of hardware or the next generation of the APIs and drivers. And finally, okay, this is all good, so we'll do some work behind the scenes for you as well as you'll do a bunch of work. So what tools do we provide? So we have a tool in DirectX SDK. It's a very powerful performance debugging tool called PIX. And I'll show you really quickly what that is. It's got a lot of features, and I don't have sufficient time to go into every aspect of it, but I'll try and show you what it does. So once you go back and download our SDK, then you can actually play with it and see for yourself what it can do. So let's just take a DirectX application from our SDK. This is a simple application that is there in our SDK. So what we did was we took something called PIX trace. And here's how you do it. So you basically open up, you create a new experiment in the PIX tool, which is part of the SDK, and you type in the name of the program, and then you choose whether you want what kind of information that you want to gather. So we gather a bunch of statistics. There is a bunch of statistics that we gather from the API automatically. We also can capture what is called a Direct3D call stream, which is essentially all the APIs, the DirectX APIs that you're calling, along with the parameters and the timing information. So I've actually done that because it actually takes a bunch of time to do that. So let's say here's, and I've loaded it up in the PIX application. So let's say I want to look at the first thing you will do is you'll look at the frame rate of your app. So this application is a little bit difficult to do on a low resolution display, but I'll give it a shot. So as you can see, so the frame rate graph is going up and down once in a while, and mostly it's steady. So let's try and zoom in into a couple of places. Let's say what's going on here. So let's zoom in further. As you can see, there's a couple of places where the performance has taken a dip. So now let's go and highlight that. So it says that it's frame 69. That's a place where your application probably glitched. So down below, it automatically highlights frame 69. And if I open it, you will see there's a bunch of, it's showing you all the various calls that have been made. So you can scroll through it. You can see all the various calls. And then there's even timing information that will give you if I scroll further. And so you can go further. So now let's say you can even try and figure out, okay, what was I drawing that caused this kind of glitch? So you can go down further, and let's say you come to a draw call here. So you can figure out what you were drawing at this time. And let's say you found that this was the place where you took most of your time. So I highlight this. So it will re-render because I have the entire call stream in the PIX app, it will re-render it and say, oh, this is what got drawn here. So now let's highlight the next one. It's saying that this is a grouping that the application created inside via some tags for the HUD itself. So if I highlight that, it shows you, so it renders and shows you the HUD coming on top of that. So go back to the draw. You can even figure out, okay, so now if we took so long, what was the problem because the meshes were too complicated? You can take a look at it, and it'll show you what you were really drawing, so what kind of meshes that you're putting in. So there's a lot more such functionality that can help you debug your application, and I will encourage you to go back and take a look at this application in great detail. So before Is it working? Okay, great. Thank you. So before I wind up the discussion on APIs, just a brief note on GDI+. It's largely changed in Windows 7, except that version 1.0 is deprecated. If you want to, you can force it via the manifest. So going ahead, DirectX is for all applications that need high-performance graphics, not just games. We are ourselves investing quite a bit on it. 10.1 is the foundation API. However, we also have two new DirectX APIs in Windows 7, Direct2D and DirectWrite. And PIX is a great tool that you should use to tune your performance in your DirectX application. And longer term, DirectX APIs will replace GDI. So now that brings me to the last section of the talk. That is talking about some of the graphic scenarios that are enabled by these hardware advances in Windows 7 timeframe. So the first one we'll look at is high color. I talked about the high color availability of high color monitors, and these are the areas of application for these monitors is quite a few places. You can do people use them in medical, visualization, presentation, photography, and CAD. So to address, for you to be able to take advantage of high color monitors in Windows 7, we have changed 3 of our APIs, the Windows Imaging Codecs and the Color System and DXGI, which are commonly used in imaging applications with 3 new formats. And these formats work in full screen and overlay mode only. The 3 formats that we've added are 10 bits per channel sRGB. So here we use the 2 extra bits per channel to give you more precision. The color gamut remains the same. Then we have 10 bit per channel extended range, or XR for short. So here we use the 2 extra bits to give you greater gamut. And in fact, the gamut range that it covers is pretty close to what a human eye can see. And we also have the best of everything, which is the 16 bit per channel HDR format. However, since it is pushing twice the amount of bits, the perf and power requirements for this is much higher. So you have to first decide what kind of challenges that you're running into. If you're doing a presentation application and you're mostly interested in eliminating banding artifacts, then you may want to use the 10 bit per channel sRGB. And if you're doing kind of or a video application with higher dynamic range or higher gamut, then you will either choose between 10 bit per channel XR or 16 bit per channel HDR, depending on your power requirements. So the next one I'll talk about is dynamic hardware changes. So I talked about the prevalence of laptops and how we all connect and disconnect monitors. And actually, we do a lot more than that. There are a number of common scenarios that are becoming increasingly common these days. So you dock and undock your laptop. So when you dock and undock, quite often the docking station may have a GPU inside it. And if you dock, of course, then you'll get the new GPU showing up. And if you undock, then the GPU vanishes. Then USB displays are becoming more and more common. And USB displays pretend as if they've got a GPU built inside them. So if you connect or disconnect, so the graphics chip comes and goes. There are other full screen applications, and this is a common scenario even today on Windows Vista. They launch, and when that happens, since it's an exclusive mode application, it takes control over the GPU, and you may not have the GPU. And finally, there are hybrid laptops, which have multiple GPUs inside them, where they use different GPUs depending upon the power. So if you're connected to the wall on AC power, you will get the higher powered GPU, and if you are running on a battery, you'll get the lower powered GPU. And this dynamic switching causes the application to perceive changes in the GPU underneath it. So if you're a GDI application, you traditionally never worried about these scenarios. And the thing that you mostly worried about in your GDI application was change in resolution, a change in mode. So you need to continue to heed the WM display change message. When you get that, you need to re-render in the new mode and change your layout to adapt to the number of pixels that are available to you. But for addressing this, for trying to detect these newer scenarios, you may want to look for WM device change message, which you will get like when some of these more drastic changes, such as laptop dock and undock happens. Now, GDI applications are fairly fine because there is a complete transparent software fallback, but it becomes more of a challenge when you have DirectX application, where you have explicit control over the hardware. So if you're writing a DirectX application, so the thing that you have to do is to check on the return value from the swap chain present call and respond based on the return code. And it could be one of the following. And there's actually some more corner cases that are documented well, but these are the common things that happen. If you get status occluded, it means that there is somebody else who's taken control over the GPU right now. So then all you need to do is just wait for that guy to go away. If you get mode change, this is very similar to like what you did before in the older versions. You reset your device and the resources that are mode dependent, and otherwise you continue. However, you can also get something more drastic, which is called device removed, and you will get that in the scenarios that I described before. So if you get that, you stop rendering and wait for WM device change message to re-enumerate the new hardware capabilities and start rendering again. Now, it turns out that there are a couple of other scenarios, thanks to remoting, and the hardware behavior that you need to be, for which you need to handle your application slightly differently. So you can get even more detailed information about why your device got removed if you call get device removed reason. And these are the two interesting scenarios there. So number one, if your GPU may actually hang sometimes, and this can happen if it's overheated or there may be other issues. And when that happens, you will get the error code saying that it got reset. And then at that point, you may want to recreate your device or give a warning and shut down altogether. Now, if you're remoting your rendering, then in which you may also get a call saying that you got a remote disconnect. And when that's basically to tell your application that you had a temporary loss in network connectivity, and then you check, and then you reconnect again. And finally, the last one I'm going to talk about is more of a fundamental, and it's high DPI. And I talked about all the various high DPI monitors and displays that are available out there today. But there's another reason why we think that high DPI is an important fundamental for all applications to address. When we ship Vista, Vista actually has, if you opt in, it will start sending an opt-in for customer care program. We start getting information about what kind of hardware configurations you have. And when we got the data, we were sort of surprised. We saw that roughly half the people were running their machines at non-native resolution. So even though the machines were capable of higher resolution, such as 16 by 12, they were not running them at that. And in fact, if you don't do that, then you tend to get very fuzzy rendering on your LCD panels. So when we dug into it a little bit more, we found that the reason why people were doing that was because they wanted to have bigger text. And I'm sure many of you have encountered that. You go to somebody's house, and then you see that it's all very fuzzy, and then you go look at the resolution. They're not running at native resolution. And that's simply because people are trying to render bigger text and for better readability. Now, the challenge is, how do you enable people to render non-fuzzy text, but yet be in the native resolution? And for that, we found that the DPI mechanism in Windows was a very convenient way to do that. And that's the reason why, another reason why we promoted the control panel to highlight the DPI change. However, when you turn on the higher DPIs or when you move to the new DPIs, we started seeing all sorts of interesting problems. I picked examples here from our own UI in Windows, but we see these kind of examples in all applications, in many applications. So you can get clip text, your layout can be busted. I mean, there's lots of interesting things that we see. Well, so in Windows Vista, we provided a very convenient way to work around these. And if your application was not DPI aware, we had a concept called DPI virtualization, where we would fake all the system metrics to your application, and your application would think it's rendering at 96 DPI. And then when we were composing the bitmaps for the window manager, we would automatically stretch them up. Of course, that brings you back to square one. Your application looks extremely fuzzy. So therefore, it turned out that DPI virtualization is really just a stopgap and not a true solution. What we really need to do is basically go and fix each of these issues. And we have done that in our own UI as well as in Internet Explorer in Windows 7. But all applications probably also have to take a look at a test and figure out how to fix these issues. So we have a pretty detailed hands-on lab where we show you how you can go from these kind of common DPI issues with this very, very simple application that we came up with to something that works on all DPIs. So I will encourage you to go and take a look at that. And we also have a couple of white papers which go into great depth about what APIs work well and how you deal with all these various scenarios, what happens if you have bitmaps and they're pixelated, what strategies do you use to load the right bitmap. There's a bunch of information that we have put into the white paper, the first white paper, which is on MSDN. And there's also a white paper, because quite often, many of our applications are trying to render web content. And to do that, quite often, the applications use the IE OCX. And IE itself has fixed that in Windows 7 with the zoom functionality. And that functionality is available for you to use as well. And there's a white paper that explains how to do that. So with that, I'm pretty close to the end. The summary is that graphics hardware is powerful, extremely powerful these days. And if used properly, tremendous end-user benefits can be realized. However, it is important to be aware of the diversity of PCs out there, and you need to adapt your applications to take advantage of this power, yet insulate it from the diversity via the DirectX APIs. So the call to action is really simple. Take a look at the DirectX APIs, learn to create rich client applications using these APIs, take advantage of the new functionality afforded by Windows 7, such as high color, make your applications robust against dynamic system changes, and address high DPI issues in the application by testing and fixing all these various issues that I showed you just before. So we have 2 more sessions that go into great detail in these APIs that I just introduced here. We have one on Direct2D and DirectWrite tomorrow. And on Thursday, we have one called Unlocking the GPU with Direct3D, where we talk about Direct3D 10 and 11, and especially and even the non-graphics part of Direct3D. And we have a hands-on lab for DirectX, which has a number of modules that I will encourage you to go. Okay, so here's the alias you could send us mail to, and I think I'm behind in schedule, but I have 10 minutes, and I can take some questions. And also, a number of us will be available at the track launch, as well as in the booth, so you can approach us there. Okay, I see a hand up there at the back. I think it would be really good if you could come to the mic and ask questions. Thank you.
For a non-3D application, what's the design point that tells a development team to leave the productivity of WPF and move to Direct2D?
I think it really comes down to trying to figure out what kind of investment that you already have and you're willing to put into the scene graph structure that you have in your application. So if you already have one, and then you really want like great performance, and then you want to have like tight control over the performance, then you would probably want to look into DirectX. But if you don't want to deal with all the various code that you have to write to manage resources or work across multiple monitors, where you have control over that, so WPF actually does a lot of that for you, and I would encourage you to use DirectX and WPF in those cases.
Is there a way to disable anti-aliasing in Windows 7 to enable small text rendering?
So you wanted to, the question was to disable anti-aliasing in Windows 7?
In order to render small text.
In order to render small text?
Yes.
Actually, I'm not sure about that. I can check, and I think there should be a way to disable anti-aliasing.
Okay, thank you.
For those of us stuck doing XP development, is there any hope of any of these APIs being brought back to XP?
Actually, right now, the XP API, there is no plan for taking these down level to XP, but it totally depends on how many people are looking for it, because it's a little bit of a challenge, because Direct3D 10 is not available in XP because the driver model is not there on XP, and the programming model in Direct3D 10 assumes that there is a driver model underneath which is doing the resource management. And so it can be done, but it's not that easy, and then at that point, it's not the same API at all. So another question.
We are using DirectX 9 with managed wrapper. Why is there no version for DirectX 10?
We are actually looking into providing managed wrappers, and we'll have news on that fairly shortly. So,
we have a video player that we don't want to have to write a whole UI for, so we're using WPF.
Right.
And there's no way to share the airspace with the Direct3D device. Wouldn't it have been fairly easy to give us a way to blend the WPF output onto our device?
Actually, WPF in the latest release, they actually support interop with DirectX, so you should be able to do that.
It interops, but we still can't. There's an airspace restriction. You know, I can create a WPF element and render into it with my DirectX, but I want to be able to I want to float my WPF UI on top of my video playback.
Okay, I'm not familiar with the interop story, so there are people from our team right here, and right at the back as well. So there's WPF folks, so they should be able to help you answer the question.
All right.
You mentioned that we might get a managed DirectX API from you guys. So what's the tension between letting XNA carry that burden, because we're going to get XNA interop in WPF versus, because it's, 99.9% managed right now, versus you guys providing us one, because after y'all dropped managed DirectX 2.0, it seemed y'all didn't really want to provide managed APIs, and y'all were going to let someone else do it.
Well, the challenge at the time was we were trying to figure out what is the right way to provide the wrapper. So at the time we originally did it at the much more lower level wrapping, which was managed DirectX. And then when we got a bunch of feedback about from the game developers, because they were the ones who were primarily beginning to use the managed DirectX APIs. So therefore, we started building on top of that with a lot more helper libraries and the kind of infrastructure that XNA provides. Then of course, it's a learning experience. Then we find that there are enough people who are using it at various levels. So what we are trying to provide is a set of tiered offerings. If we provide managed wrappers, so if you really want to stick to the low level, then you use the managed wrappers in DirectX. If you want to do something which is very portable on cell phones and write games, which are casual games which work on cell phones, Xbox, a PC with sort of a mini game engine, then you would use XNA, and WPF for all the UI-centric applications that are out that it is being evangelized for.
Yeah, are we going to have airspace issues if you guys give us a managed wrapper? How's that all going to work? Because that kind of got solved in Service Pack 1 with at least 3D content, maybe not video content like that guy was telling. So are there going to be any airspace issues if you guys provide us a managed wrapper and we try to use it in WPF?
I do not believe so, but we will definitely take a look at it when we get to that point. That we don't intend to have interop issues like the way it was before. So we want to make it all work together.
Thank you.
I'm using DirectX 9 to do 2D rendering and text, and one problem that we see with our application is if you have multiple graphics cards, like for a 3-monitor system, as you move these windows to the other monitors, you get huge performance degradation because it's copying between the different graphics devices. Does Direct2D and DirectWrite solve these problems?
No, those problems continue to exist with even DirectX 10 because that's more issue of hardware, like you are actually literally copying stuff from across the various pieces. But I think that there are some improvements that we have made in our driver model in Windows 7. And if you come by our booth, I'll find somebody who can talk to you more about it.
Thanks.
Your slide mentioned there's DirectTV is the software implementation as well, right? So will that be available as an API that I can use just a software implementation in previous versions of Windows that aren't 7?
Yeah, you can use it on Vista. We're going to provide you on whatever we have on Windows 7, that will go down to Vista.
Okay.
So you can use it on Vista.
Now, what about XP, though?
XP, we don't yet have a plan for being able to take it.
But if it's a software-only implementation, there's not going to be any dependencies on the hardware. So
we'll look into that. We will look into that. So currently, we don't have a plan to take it down to XP. But if that is something that is desired, we'll definitely look into that.
I definitely would find it very useful.
Okay. Okay. So if there are more questions, I think a bunch of us will be available at the Ask the Experts as well as at the booth. So happy to take more questions there. Thank you very much.